are the learning objectives for today. So we're going to define radiation, radioactive decay, activity, and half-life. And these are just definitions, so the best way to learn them, I'm sure I've mentioned this to you guys already, is just through flashcards. Flashcards are always the best way to learn definitions because they're just rote learning. Know that there are several types of nuclear radiation, including the alpha particle, beta particle, a gamma ray, and neutrons. So, now you know. Obviously, we're going to go into the detail of what each of these consists of throughout the lesson. So, know that different types of radiation have different penetration ranges and ionizing power. And to understand and write nuclear equations to represent radioactive decay. So this is one of the learning objectives that a lot of people do struggle with, but hopefully by the end of today that'll be quite clear and easy for you to do. And also know that radioactive decay and radioactive decay is random, and relate this to half-life, and also to determine half-life from data. Okay, so half-life is a relatively big topic from the things that we're going to go through today. And it's one of those ones where they will always give you a graph and ask you to interpret it. And that in itself is what makes half-lives a relatively more difficult topic because of the fact that graphs are involved. So hopefully we'll try and illustrate how to do these today. So for those of you that would like to know, for EQA, we're going to be going through the exam board specification point 4.4.2. For OCR, we're going to be going all the way from P6.1E to P6.1H. And from EdXL, we're going to be going through 6.1 all the way through to 6.27. So we're actually covering a lot of the specification points from EdXL. Okay, so this is your starter task to get you guys woken up. How many protons, neutrons, and electrons are in this atom of uranium? So have a go at this at home, and I will give you a minute to have a crack at it. Okay. So there are 45 seconds left. So remember, these different numbers on this thing that's been lifted off of the periodic table have different meanings. So the key to being able to answer this question is to remember what are the different meanings of each of these numbers. So what does the 92 represent? What does the 238 represent? Or 238.03? Okay, so you've got a grand total of 5 seconds left, and that will probably do. Okay, so let's talk about this big number on top first. So this, for those of you that remember, that's amazing, but in case you couldn't, so this is known as the atomic number. Atomic number. Okay, am I right? It might be a tiny bit small, but hopefully that's legible. So atomic number, that tells us the number of protons in an atom. Okay, and because an atom is uncharged, an atom has no charge on it, remember, it's just a neutral atom. Okay, because this atom is uncharged. Remember, a charged particle would be an ion. So an uncharged atom will have the same number of protons and the same number of electrons. Okay, so therefore there are also 92 electrons in this atom of uranium. Okay, so now onto this big number here. So this is known as the mass number. Okay, so the mass number. So there's only one thing really left to figure out. Well, that's the neutrons. So how can I use the mass number to figure out the number of neutrons? Well, remember that electrons are essentially, they're super tiny. atoms in general are super, super tiny, and protons and neutrons are also super, super tiny. But the electrons are even smaller than that. Okay, so we would not consider them as adding to the mass at all. What we would consider as adding to the mass are the number of protons and the number of neutrons. So the mass number is equal to the number of protons plus the number of neutrons. So if I know now the number of protons, I can just do the mass number 238 minus 92, and voila, I've got the number of neutrons. I'm going to do that on a calculator because I don't want to make a mistake. So that is 146. Amazing. So protons is number of neutrons. Protons is 92. Electrons is also 92 because remember, number of protons equals the number of electrons in an atom. This is not true necessarily in a charged particle such as an ion. And remember, we spell ion with I-O-N. So if there is a charge on the particle, it is a completely separate kind of ball game. And the neutrons are going to be the mass number minus the proton number to give us just the number of neutrons. Okay, so the reason that I chose uranium for the starter task today, and this is a starter task in general, was because uranium is a type of radioactive material. It will be constantly decaying, giving off alpha, gamma, beta radiation, etc. Okay, so here is the first Slido. Let me see. If you could ask you guys to make a note of the numbers on this atom radon. So it is 86 and 22. I'm not going to tell you which one's which. I'm hoping that you guys can remember. So 86 and 222. So how many protons are in one atom of radon? And just remember, it was 86222. 86 was the number on top, and 222 was the number on the bottom. So just scan the QR code to join. Or go on to slido.com and type in the number 102862. So I'll give you a chance to do that because there are a few of you on. '86. Okay, we've got 1 for 86. Oh, actually, sorry, we've got 6 for 86. Oh, you guys are smashing it. Okay. I have no idea what that L's means, but 86 it just seems to be getting bigger and bigger and bigger. So congrats, guys. Yeah, 86 is the correct answer for the number of protons in the atom of radon, because obviously, like we said, the atomic number just represents the number of protons. Yeah, so the atomic number will represent the number of protons in the atom. And I feel like that whoever's put 68 is very close, but potentially type them in the wrong way around. Okay, so that will do. All right, so moving on to the number of electrons in one atom of radon. I remember the number was 86 and 222. Seriously keeps on thinking I'm talking to it, but I'm not. Okay, some people think again it's 86. 86 is getting bigger and bigger and bigger. Okay, so this is the number of electrons in the atom. Okay, so we have got quite a few dozen votes for 86, hence why it's so much bigger. And again, you'd be right, because like we said, the number of protons equals the number of electrons in an atom. And finally, have a crack at this. So remember the numbers were 86, so 86, and 222. 222. Okay, this one seems to be. I'm gonna guess that the 86 was accidentally someone typing it in from the last one. Fun. I really hope so. Okay, so 222 and 86 were the numbers, and then 136 just seems to be getting bigger and bigger and bigger. Amazing, yeah. Okay, so 136 has got the most votes by far. Well done, everyone. And you'll be right. So obviously, to get the number of neutrons in an atom, we would take the mass number, which is the big one, minus it from the atomic number, which is the littler one, and well, boom, you're left with the number of neutrons in the atom. Okay, so how do I change this? Fine. Okay, and again, radon is also another radioactive material, hence why we chose it. So, before we go any further, could I just gauge how confident do you guys feel about nuclear radiation? Okay, so relatively even split between the fives and the ones. So it really doesn't matter where you guys sit right now. Our aim is to hopefully try and push everyone that's anything below a five all the way up to five or four. And anyone who's already sitting at a five to help you consolidate your learning and hopefully help you make sure that by the time your exams come around in little over a year's time now, hopefully this will still be in your memories. Okay, so we've had 33 responses, and it seems like 4 out of 5 is the most common. And just to clarify, 5 out of 5 is the best one. So you're super confident. You're a nuclear radiation wizard, whereas 1 is the opposite. So you need more practice. And how many of you guys are here? Okay, so I'll just wait for a few more responses just so that we can see, engage. Because to be fair, this will guide how quickly I go through things and how much we spend on questions. Okay, so that will probably do. We've got most of you are really confident, so we're around the 4 mark for 45% of you. But there are roughly another 45% of you that are on 3s and belows. So hopefully we'll try and go at a moderate pace and try and case it for everyone. Okay. Okay. So radiation is defined as the emission and transmission of energy. Okay. So this can be in the form of waves or particles through space or through a material medium. So what do we mean by emission and transmission? So they're essentially relatively similar words to one another. So they're just means that we're putting out. Okay, so just think of them both as putting out energy. Okay, so emitting or transmitting energy. So waves, as we'll go on to find out, would be gamma waves, and this is the symbol for gamma. Okay, so all of our electromagnetic radiation that are waves tend to be gamma waves, or particles. Remember, we can get alpha particles or beta particles. Okay, so these are particles of emission, so they're actually solid things in the, if we could get a microscope and zoom in, we'd actually see little particles. I don't think there's probably a microscope big enough, but if you could get one, you would see that. Whereas in gamma rays, they're waves, so they're not necessarily something that we can physically see, but they're things that we can detect, right? And the gamma waves will be something that you will study when you go through electromagnetic radiation. because that's a huge part of the electromagnetic spectrum, and it's really, really important and serves loads of purposes. So this little image is just kind of to illustrate when we emit or transmit waves or particles, not all of them will pass through physical barriers such as blocks of lead. Okay, so different particles and different waves will have different penetrating strength. Penetrating strengths. Okay. So particles, if you think about it, actually, have a guess at which one in your head would be more likely to penetrate through things versus what wouldn't be. Well, obviously particles are actually solid particles, right? It would be like me hurling a tennis ball at a wall and expecting it to go through. Then highly unlikely to go through. Yeah, because they're actually solid parts which can be stopped by a few centimeters of lead or paper, etc. And these are one of the properties of different forms of radiation, and we'll go through each of the properties and some others in more detail. Okay, so like we said before, so particle radiation, such as alpha radiation, beta radiation, gamma radiation, and neutron radiation, are what we will be discussing today. So alpha, beta, gamma, and neutron. So neutron is a new thing that we're only going to touch on, I think, for not too long, but the main focus will be alpha, beta, gamma. Okay, so radioactive decay is the process by which an unstable atomic nucleus loses energy by radiation. Okay, so when this atomic nucleus, so if a nucleus has loads and loads of protons compared to the number of electrons, or if it's got loads and loads of electrons and not enough protons, the nucleus is unstable. Okay, it wants to become more stable because then it's like it's balanced. And the only way to do that is by releasing some of the energy housed within the unstable nucleus. Okay, so losing the energy in either the form of alpha, beta, gamma, or neutron radiation means that there is less energy left in the nucleus, and this makes the nucleus more stable because the nucleus can carry the amount of energy that it has. So radioactive decay occurs when a nucleus from an unstable atom breaks down and emits ionizing radiation. Okay, the one exception to this really is gamma, where the nucleus doesn't really break down as such. What happens in gamma radiation is a very similar thing. Remember, it's an unstable nucleus and it's got a lot of energy that it doesn't really want anymore. It wants to get rid of this energy. So what will happen to it? Well, it will just emit a gamma wave. Okay, and that gamma wave will just take the energy away from it and move on. But remember, it's not actually like the nucleus is breaking down into its constituent parts. What's happening is just an energy is just being lost. That's all. In the form of a wave. Okay, so here is a diagram of an unstable atomic nucleus. And here is what can happen when it undergoes radioactive decay. So we have a particle being emitted and some energy that is being released alongside it to counteract it. Okay, so to obviously release a particle, that particle will have energy with it. At the bare minimum, it will have kinetic energy with it. So this energy, when it's when the particle is released, is taking it away from the nucleus, leaving the nucleus with less energy and making it more stable. Okay, and you'll find that this is what all chemical reactions are really trying to do. They're trying to become more stable. Okay, so let's crack on. So radioactive decay is also known as nuclear decay or radioactivity. So these are just other terms that also mean the exact same thing. And materials containing unstable nuclei are considered radioactive. So things like your uranium that we spoke about earlier, things like your radon that we mentioned earlier. So these are all going to be different molecules that are actually radioactive because they tend to have an unstable nuclei. They tend to have either too many protons for the number of neutrons or too many neutrons for the number of protons. So these reasons make these atoms or make these elements, when we find them in the earth, they tend to be relatively radioactive and constantly emitting radiation. Okay, and this radiation is not always a bad thing. We've harnessed it for some pretty useful uses, but we'll go through that towards the end. Okay, so remember this concept of an unstable nucleus is not one that's super common, right? So most of the atoms that we see in everyday life, you know, the atoms that you're made out of, the atoms that your table is made out of, or your bed, or your chair, or your sofa, these are all really, really stable. They don't really change unless we stress it a lot and do some sort of chemical reaction upon it. These atoms won't really change because the nuclei are super, super stable. But the atoms of a radioactive substance have an unstable nucleus. Okay, and it's just these radioactive substances that have these unstable nucleus. And this unstable nucleus is never happy. It wants to become stable. Because why wouldn't you? Imagine if you were just teetering on a skateboard or something. Of course, you're going to either fall off or, well, you'll probably fall off. Yeah, and by that point, you'll be stable. And so that's what the atom really wants to do. It just wants to fall off, lose a bit of energy, and become stable so that it doesn't have to constantly be teetering on a skateboard. Okay. So nuclei with too many or too few neutrons exist naturally, but are unstable and will decay quickly by emitting radiation, which is exactly what I mentioned before. Remember, too many neutrons in a nucleus or too little neutrons in a nucleus will lead to an unstable nucleus. There's got to be the right amount. They've got to be balanced. The proton number and the neutron number have got to be balanced, not equal to one another. That necessarily doesn't have to be true, but and it's not something that you're ever going to be asked to figure out, how many neutrons does this need to be stable? That's not something that you'll ever be asked to figure out, even at A level. But this is just a matter of fact, really. So if there are too many neutrons, it can become unstable. If there's too little neutrons, it can become unstable. So remember, unstable nuclei will disintegrate, and this will be its radioactive decay. Okay, so it's interesting that so make sure you pick up on the fact that we're talking about neutrons here. So number of neutrons versus the number of protons. So we would call the number of neutrons too many or the number of neutrons too few. And why is it not the number of protons that are specified here? Why is it not the number of protons? Well, it's because the number of protons is what dictates what an atom is. Yeah, so which element an atom will belong to. So if we say that we have to change the number of protons for this atom to become more stable, what we'd have to do then is change the atom itself. We'd be changing some of the fundamental properties of this atom by changing the number of protons. So which is why we kind of tend to revolve around thinking of the number of neutrons as being the ones that are unbalanced. Okay, so the number of protons, remember, dictates exactly what the atom is. So for example, carbon will have 6, oxygen will have 8. No oxygen atom will have 24 protons, because it will no longer be oxygen. It will be a completely different element, which I don't know off the top of my head. So carbon, remember, every carbon will have exactly 6 protons, because any more or any less than that, and it's no longer carbon, it will be a different element altogether. So that's why we think of the unbalanced nuclei as revolving around the number of neutrons, either too many neutrons or too few neutrons, because if we change the number of protons, if there are too many protons, that doesn't really make sense, because they're no longer the same element. Okay. So the nucleus will become stable by emitting alpha or beta particles and then cool down by emitting gamma radiation. Okay, so an atom's nucleus is stable if it has a certain number of neutrons related to the number of its protons. Okay, fine. Let me just check how we're doing for time. Okay, amazing. We've got ages. Super. So yes, so remember, we will emit an alpha particle or a beta particle. Okay, so for those of you that are already curious and don't want to wait until later, an alpha particle is what we would call just a helium nucleus. Okay, so it's a helium nucleus essentially, which is basically just 2 protons and 2 neutrons. So we'll have a mass number of 4, an atomic number of 2. Okay, and we can also represent it without using the word helium. We can just write the symbol for alpha and put a 4 and a 2. Okay, so alpha, 4 and a 2. And that is an alpha particle, because an alpha particle is a nucleus, essentially. A nucleus or a particle of 2 protons plus 2 neutrons. So it gives it a mass number of 4 and an atomic number of 2. A beta particle is just an electron. Okay, so it'll have a charge of -1, and that's it. Yeah, no atomic number, no proton number, no mass number. Yeah, it will just have a charge of -1 because it's just an electron. Something else exciting happens in beta decay, where a proton will change into a neutron. But that's not what the beta particle itself is. The beta particle is just an electron. Okay, so these are the 2 types of alpha. These are alpha and beta radiation. Remember, gamma radiation is just a gamma wave. Yeah, so it's just a gamma wave, and the atom itself, apart from losing energy, none of the number of protons are different, none of the number of neutrons are different, and none of the number of electrons are different. Okay, so the gamma radiation is just purely energy being shot off in a particular direction. Okay, so elements that have fewer protons will be stable if they have the same number of neutrons and protons. Okay, so if we can match the ratio of protons to neutrons in these smaller atoms that have fewer protons, they're stable. So, for example, carbon-12. Okay, so carbon-12, you can see that there are I'm going to say that these red ones are neutrons, the blue ones are protons. So you can see that carbon-12 has 1, 2, 3, 4, 5, 6 neutrons and 6 protons. Okay, and therefore this would make it stable because 1, it's a small atom with only 6 protons, and 2, the number of protons and the number of neutrons match. Okay, so when we start to get bigger and bigger and bigger, when the atom starts to get bigger and we start to get, I don't know, 50, 60 protons in the nucleus of the atom, we tend to find that the number of neutrons tends to go up rapidly. So they're very rarely 50 neutrons as well. We can find that the number of neutrons will be a lot higher. And this tends to make it unbalanced. They become very neutron heavy. And remember, the opposite will be also true if we find an atom that has too few neutrons for the number of protons. That would also be an unstable atom. So let's have a go at a Slido. So what makes the nucleus of an atom unstable? So there is a grand total of almost 100 of you. So I'm going to wait a little, try and get the majority of you in for a response. Oh, I'm going to try and hide the answers. That may or may not have been the correct answer. Think on your feet, guys. All right. So what makes the nucleus of an atom unstable? So is it a nucleus with more protons than electrons? Is it a nucleus with too many or too few neutrons? Or is it a nucleus with too many or too few neutrons? So what is it that makes the nucleus of an atom unstable? So we have got 38 responses. So I'm going to wait for roughly around 50-ish, and then we will march on. Okay. So this is not a tough question, hopefully, because I've been repeating it dozens of times since we've started. But hopefully it will, help to consolidate your learning. Yeah, it's just to kind of recap the things that we do as we go along. All right, if I can get one more, I will take it. Amazing. Okay, so what does make the nucleus of an atom more stable? Yeah, exactly. So a nucleus with too many or too few neutrons. Exactly. So I do think the other two have valid arguments against it, but it's just because that this question itself specifies what makes the nucleus of an atom unstable. So a nucleus with more protons than electrons, or a nucleus with too many or too few electrons, remember, would be an ion. And ions are relatively reactive. They want to go, and you won't just find an ion sitting around by itself, because it's got a charge and it'll be attracted to anything around it that may also have a charge. So they're relatively reactive, but that's not really what makes that wouldn't mean necessarily that it's unstable. An ion doesn't want to break down and become something else to become more stable. An ion won't undergo decay. Whereas an atom with too many or too few neutrons, the nucleus itself is unstable. It's not just that it's reactive, but it's unstable, which is why the top answer, which 92% of you got, is correct. So super. So let me see if we can stop this. Amazing. Okay, so radiation and radioactive decay. So, but as the number of protons increases, more and more neutrons are required in order to keep the nucleus stable. So, for example, lead-206 will have 82 protons and 124 neutrons. That's more than 1.5 times the number of protons as neutrons. So it's no longer matched. Okay, so the more neutrons are required, the more we go, the more the number of protons increases. So remember, when it's small atoms, like for example, carbon-12, we have an equal number of protons and an equal number of neutrons, because that is the most stable nuclear configuration for smaller atoms. As the atoms get bigger and bigger and bigger, so for example, lead-206, which has 82 protons compared to carbon-6, lead-206 has 82 protons, and this means that to be stable, it can't have the same number of protons and neutrons. It must have a slightly larger number of neutrons to stay stable, which is why it has 124, which is over 1.5 times the number of protons. So these are, anyone know what the term for this is? For these different molecules? So this is carbon-12, this is carbon-13, and this is carbon-14. Does anyone know what term I would use to describe all three of these collectively? Anybody know? So have a little think to yourself, maybe write it out if you are confident, because the thing is, you want to make sure that you get the spelling right of these words as well. So I'll always encourage you to write anything out that you would be shouting out in a class. Okay, so these would all be called isotopes. Okay, and these, if we look at them, what is the difference between carbon-12 and carbon-13 and carbon-14? Well, is it the number of electrons? So there's 6 there, there's 6 there, and 6 there. So it can't be the number of electrons. Yeah, the number of protons. Well, there's 6 protons, 6 protons, 6 protons. Because remember, if it wasn't 6 protons, it would no longer be carbon. It would be a completely different element. So all of this would be, well, useless. So the thing that is different between each of these different atoms is the number of neutrons, and this should be NEUTRONS. Okay, number of neutrons. So it will be 6 neutrons, 7 neutrons, and 8 neutrons. And which is why these are called carbon 12, because 6 plus 6 is 12. Carbon 13, because 6 plus 7 is 13. And carbon 14, because 6 plus 8, sorry, is 14. And this, these numbers essentially represent the mass number of these different isotopes. So isotopes are atoms of the same element, but have different mass numbers. Okay, so same element, but different mass numbers. Okay, mass numbers. So you will probably learn about this more in chemistry, actually. So chemistry is very, very heavy on isotopes. It loves to talk about isotopes. So when you get through to this topic in chemistry, you'll become more clear, and you're going to do loads more questions on it. But remember that an isotope is just the same element, so carbon, 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 but with different mass numbers, so 12, 13, and 14. Okay, so the 3 main types of ionizing radiation emitted by the unstable nucleus of a radioactive atom is alpha decay, and this is the symbol for alpha. I tried to draw it out earlier, but it might have just looked like a little bit of a scribble. And this is a beta decay, so very similar looking to a capital B itself. And gamma decay, so gamma, easiest to go like just draw like that. Okay, so alpha decay, beta decay, and gamma decay. So remember, alpha is your helium nucleus or an alpha particle. Your beta is just an electron or a beta particle. And remember, in the nucleus, sorry, something funky happens. So a proton will then become a neutron in the nucleus, and this will cause the emission of the beta particle or the electron, in other words. And gamma radiation or gamma decay is just a photon or a wave. Okay, so all of these types of radiation involve emitting one or more particles. So gamma waves or gamma decay, remember, isn't really a particle, it's more of a wave, but that's fine. Okay, so to summarize, the radiation includes particle radiation such as alpha radiation, beta radiation, gamma radiation, and neutron radiation. So radioactive decay occurs when a nucleus forms from an unstable atom, breaks down and emits ionizing radiation. So we'll go through these words and what they really mean in just a moment as well. So like, for example, ionizing radiation is not really one that we've discussed at great length. And materials containing unstable nuclei are considered radioactive. So radioactive meaning that they're just going to give off radioactive emissions. They're going to break down, the nuclei will break down and give off these particles as emissions. And the nucleus will become stable by emitting alpha or beta particles and gamma radiation. Okay, so alpha or beta particles and gamma radiation. So just before we go any further, remember what let's try and think of, so that we're all on the same page. Let's think about what the term ionizing radiation means. Okay, so what does the term ionizing mean? Well, what is an ion? Anyone remember? So have a little think to yourself, what is an ion? Well, an ion is a charged particle, and like we said, they're reactive. We mentioned this earlier. Charged particles are reactive, so they don't want to just sit around and relax and take a stroll through the air. They want to go out and they want to react with something else because they're charged. They're not hugely stable themselves. So what does this mean, ionizing radiation? Well, they're just going to ionize previously neutral compounds, and previously neutral atoms that weren't hugely reactive, that were quite stable. The radiation will come, an alpha particle will come along, and it'll just hit the atom and knock off an electron. And this will leave this atom that we just saw, or we spoke of, with an electron less, or maybe it will knock off a proton, and that will leave it with an electron too many. And this makes it an ion, because there is an imbalance between the number of protons and the number of electrons. So it will be a charged particle with either a negative or a positive charge. And these charged particles, like we said, are very reactive. So it's not good to have ionizing radiation come and hit normal atoms, and for us to be around that, because it's particularly not good for our cells, as they can cause many diseases. Okay, so we have to be careful around radiation. Okay, so now to define activity. So activity in the radioactive decay process refers to the number of unstable atomic nuclei that decay per second in a given sample. So there's a lot of words there, so just take it in for a minute. So activity is basically a measure of how active a radioactive nuclei really is. Okay, and it will tell us how many decays a second is in a given sample. So the more decays, obviously, the more radioactive a particular substance is. Okay, so the more decays, the more often it's giving off an alpha particle or a beta particle or any sort of similar particle to remember, lose energy and become more stable in itself. Okay, so alpha activity tells us how radioactive it is. How often is this decaying, and how much does how dangerous is it, essentially? Okay, so it is measured in a Backroll, BQ, capital BQ. So 1 Backroll is actually a very, very small amount of radioactivity. I can't remember exactly what the number of Backroll it is, but there is radioactivity all around us. We're constantly being bathed in radioactive emissions, but they're just very, 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 it's a very small amount, which is why it's not too dangerous, and we live till the age of 80, 90, 100. But and it's probably way more than 1 Backroll. So just to give you a measure of quite how small 1 Backroll really is. Okay, so Geiger Muller counters, which is one that we've got here, are the instruments that we use to measure radiation. Okay, so obviously we can't just sit there and count the particles that are coming off the radioactive material. We use Geiger Muller counters, and I would imagine that this was made by some guy named Muller and some person named Geiger, and they came up with this counter. And this counter will have little windows in it where you can point it towards a radioactive source, and the radioactive emissions will come out, and it will go through the tube, and it will hit the walls of the tube, and the tube will register this as little tiny electrical interferences, and that the tube will essentially count the number of interferences and then give you, oh, okay, this is a Backroll of 50 or 100 or I don't know, million or any number. Okay, so the count rate is the number of counts per second. Okay, and this is proportional to the activity of the sample. Okay, so the more active a sample is, the higher the count rate. Okay, so the number of counts per second. Okay, so remember, Backroll is a different unit. Backroll BQ is a measure of radioactivity. Okay, is a measure of radioactivity, and 1 Backroll is a very small amount of radioactivity, whereas Geiger Muller counters are counters that measure the number of counts per second, so the number of decays per second. And this is proportional to the activity of the sample. So although they're related to one another, they're not necessarily the exact same thing. Okay, so what is the activity number of a source emitting 2,400 particles in a minute. Okay, so the activity number of a source emitting 2,400 particles in a minute. And this is the, oh, okay, so this is the question. I think I've hidden the answer now. So if I could get you guys to join in. Okay, so 20 responses, which is not great. I think I'll wait for at least 30. Surely we can get to a 30, guys. Okay, so what is the activity number of a source emitting 2,400 particles in a single minute? So will it be 2,400 Backroll? Will it be 400 Backroll, 40 Backroll, or 60 Backroll? Okay, so let's think back to exactly what is the actual thing that Backroll represents. Well, a Backroll refers to the number of an unstable atomic nuclei that decay per second in a given sample. Okay, and we're told that this source emits 2,400 particles in a minute. So hopefully this is a hint for you guys. Okay, so remember, a Backroll is the number of unstable atomic nuclei that decay per second. This is a number of particles that is in a minute. We've been given particles in a minute, and we essentially just want particles per second. Okay, so we've got 40 responses. I'm going to take that. Thank you to everyone that participated. And it is 40. Okay, so how do we get to 40? Obviously, 2,400 divided by 60. And let's see what you guys put. Okay, so the majority of you got that right, which is really, really great. And I'm really happy to see it. So for the others that didn't and went for 2,400 Backroll, always funny, as soon as you open up the, as soon as you show what the answer is, it floods in with a few more answers. So, yeah, so 2,400 Backroll is not the correct answer because 2,400 Backroll would mean that there are 2,400 particles in a second. Well, we've just been told that there are 2,400 particles in a minute. So if we have 2,400 particles in a second, that's a hell of a lot more particles in a minute rather than the same number. Okay. So to find the answer, obviously we take the 2,400 because that's in a minute and divide it by 60 to get the number of particles in a second. Okay, so stop that. Fine, moving forward. Okay, so now we're going to start talking about half-lives. So half-lives are a really interesting topic and they're relatively difficult. Okay, so half-lives are actually a difficult part of radiation, I think, because it's difficult to wrap your head around it. So the half-life of a radioactive isotope is the time it takes for the number of nuclei of the isotope in a sample to halve. Okay, so for example, where is my pen? There we go. So say I've got 100 radioactive nuclei. Okay, so the half-life is a time. We're measuring a measurement of time. Okay, so is the time it takes for this 100. And remember, it's an unstable nuclei of loads and loads of neutrons and not enough protons. So it's going to want to decay. Okay, and over time, it will decay. Okay, so I will go from being 100 neutrons to 99, then to 98, then to 97, 96, 95, etc., etc., etc. So the half-life is the amount of time t it will take to go from 100 to 50. Okay, so from 100 to 50. So that time t, again, have a think. Where will it be if I wait for another time t? So if I wait for the exact same amount of time as I waited to get to 50 the first time around, where will I get? Will I get to, well, there's essentially two options, right? So will I get to 0 or will I get to another number? Okay, I think by the way I've just phrased the question, it's probably relatively obvious. There's going to be another number. Okay, so if I wait for a certain amount of time t, and I go from 100 to 50, that's half, yeah? So if I wait that same amount of time t again, and I'm going from 50 to whatever the next number is, I'm going to be again reducing the amount of atoms that are unstable and trying to decay by a factor of a half. So if I had 50 before, I will now have 25. I hope that makes sense. Okay, so if the half-life is the amount of time it takes for an isotope in a sample to halve. And if you didn't quite get that, not to worry too much because we're going to go through it in a little bit more detail just now. Okay, so remember, this means that half-life is the time it takes for the count rates also, or the activity, to fall to half its level. Okay, so it's a good thing to bear in mind. Okay, so it's not just the number of nuclei that will halve, but if the number of nuclei halve, then naturally the activity is going to halve, or the count rate is going to halve, okay, because there are less active atoms in the nucleus that are trying to decay and give off this nuclear radiation. Okay? So alpha, beta, gamma, etc. So half-life. So let's have a look at this. Okay, so this is phosphorus. Phosphorus, remember, is one of the elements on the periodic table, and we can get radioactive isotopes of phosphorus. Okay, radioactive isotopes of phosphorus. So what happens when we have a radioactive isotope of phosphorus? Well, it will decay just like any other radioactive material will. And when it decays, it will give off alpha particles. So remember, an alpha particle will be your nucleus of a helium nuclei. Okay, so a helium nucleus essentially. And that will involve having 2 protons and 2 neutrons. So it will have an atomic number of 2 and a proton number of 4. So let's say I have, I don't know, a random element X, and it's got 94 as the mass number and 27 as the proton number. Okay, well, what will happen to the symbol and the thing on the periodic table for X after it gives off an alpha particle? Will it just remain the same, or will it change? Will it look different? Well, of course, it's going to look different because it's just lost 2 neutrons and 2 protons. Yeah, so easiest thing is, and also because it's lost protons, it's now going to be a completely separate element, because remember, the number of protons is what dictates which element an element is. Okay, so it had 27 protons, and now it's just lost 2, therefore it will have 25 protons left over. That means they will no longer be this random element X. It will be some other random element, and I don't know what exactly has 27 protons, so I'm just going to say Y. Okay, it's just going to be a random element Y. Okay, and the number of neutrons and protons, or the mass number in other terms, is going to go down by how many? So remember, we've lost 2 protons, and now we've lost 2 neutrons. Okay, so I've accounted for the lost protons. I've gone from 27 to 25. What's the mass number going to be? Well, some people here will make the mistake of saying, okay, so we've already thought about the protons, so that must mean that there are only 92. There's 92 left in the neutrons, because in the mass number, sorry, because we've already thought about the protons. We don't need to think about the protons anymore. Well, that's not necessarily true, because the mass number, remember, is the protons plus the number of neutrons. So the mass number of this new element Y will actually still include the loss of the proton. So it'll go from 94 to -4. Yeah, not 2 minus 4, but we'll take off 4. So it will become 90. Okay, so it will go from 90 to 90 is the mass number and 25 is the proton number, and it will be a completely different element itself now, because remember, the number of protons dictates the element an atom will belong to. So if we no longer have 27 protons, it will no longer be this random element X, yeah? It will be a completely different element. Okay, so that was all to kind of point out that when phosphorus decays, and it decays via alpha radiation, it's going to change into a different element, okay? And it will go into sulfur. And we're going to represent sulfur as this orangey brick red kind of color, okay? So at 0 days, this is our sample of sulfur 32. Sorry, phosphorus 32. Okay, so we've got 100% phosphorus 32. And then at 14 days, we see about this much phosphorus 32. And all of a sudden, really oddly, we've also got some sulfur 32. Okay, and there's a certain amount of sulfur 32. And then we wait a little longer and we see that the amount of sulfur 32 has grown even more. Okay, it's not grown by as much as it did in the first 14 days, but it's grown by even more than it had before. Okay, so the amount it's increased has not increased hugely, but it's still increased. And then at 48 days, there's even less phosphorus 32 and even more sulfur 32. Okay, so what do you think is the half-life of phosphorus 32, which is obviously the element that's decaying here? Yeah? It's the phosphorus 32 that's unstable and is decaying via alpha radiation or potentially even beta radiation, and is becoming a different element. So what is the half-life? Well, the half-life will be exactly 14 days, okay, because that is how long. This is roughly 50%. This is roughly 50%. Okay. And then here, this much is roughly 50% of what was left. Okay. And then if we go over here, this is roughly 50% of what was left again. So you can see that every single time is getting the amount of phosphorus is going down by 50% every 14 days, okay? And every 14 days it resets. So the first 14 days it goes down by 15%, 50%, and then the next 14 days will go down by another 50%, and the next 14 days will go down another 50%. And then if we had one in another 14 days at 62 days, we will see that there'll be this much phosphorus. That was actually a really good line. I'm really impressed with that. There we go. So that is 50% of phosphorus gone again, and that would be at 62 days, because that's another 14 days onwards. Okay, and I'll just keep on going, keep on going, keep on going. Okay, and the number of sulfur 32 particles, not sulfur, sorry, phosphorus 32 particles, will keep going down and keep going down and keep going down.